Hello and welcome. In this lecture we are going to look at some more details of 2's complement representation of signed integers. Here is a quick recap of some topics related to this lecture that we have seen earlier. We have seen how integers are represented in a computer, and we have seen this for both unsigned integers and signed integers. In this lecture we are going to look at a bit more closely at 2's complement representation for signed integers. We have already seen this earlier slightly sketchily. We are going to look at it a bit more closely today, and we are also going to see how the magnitude of negative integers represented in 2's complement representation can be computed. So now for signed integers we have already seen that we could treat the most significant bit as the sign bit, and if the most significant bit is 1, then we could treat the integer as a negative integer, and if the MSB is 0 we could treat it as a positive integer. This representation is also called the sign magnitude representation for obvious reasons, and we have seen similar examples earlier where here I am trying to represent integers using 3 bits, and I have arranged the integers along a circle. As an unsigned integer this represents 0, this represents 1, 2, 3, 4, 5, 6, 7. So I have represented the binary representations of these unsigned integers along this circle in this order 0 to 7, and now I want to interpret these sequences of zeros and ones as 2's complement representation of integers. So here are the MSB 0 representations, here are the MSB 1 representations, and in the sign magnitude the MSB just gives you the sign, the rest of it gives you the magnitude. So we have seen that this corresponds to plus 0, plus 1, plus 2, plus 3, and then minus 0, minus 1, minus 2, minus 3. We have also seen that this basically corresponds to 2 increasing directions, one in this way and the other in this way. These are 2 different increasing directions, and it also gives rise to this wasteful representation where we have 2 representations of 0. Now before we go to 2's complement representation, we would like to ask that, well, how else could we represent negative integers in binary? So using the MSB to represent the sign is really convenient, because we could just look at one bit and tell whether the number is positive or negative. And so here is our circle again, and if we say that our MSB still represents the sign, so we know that these are plus 0, plus 1, plus 2, plus 3. Now what about these? Here the MSB is 1, and so these must represent negative integers, but what negative integer should we let each of these sequences of zeros and ones represent? So for example, what negative number should 100 represent, what should 111 represent, and so on. Now in trying to answer this question, what we might want to think of this circle as a wrapped around number line. So if you think of this circle as a wrapped around number line, then I can see that from here to here the numbers are increasing, plus 0, plus 1, plus 2, plus 3. These are going to be negative integers. So can I somehow think of this circle, can I somehow unwrap this circle into a number line such that along the number line I get 0, 1, 2, 3 at these positions, and these correspond to negative integers, and still I can think of the unwrapped circle as a usual number line. So in order to break up a circle into a number line, we have to figure out where to break this circle. Now there are 2 logical points to break where the MSB is changing. So this is one point where I am going from 1 to 0, and this is the other point where I am going from 0 to 1. Now if I broke the circle at this point, then I would get a number line which starts like this 0, 1, 2, 3, and then there are 4 numbers which, if I assume the MSB to be representing the sign, should be negative numbers. So my number line would now look like this, right? So I have broken the circle here, so I get 0, 1, 2, 3, and then I get these numbers with the blue MSB. And if I want to treat this as a number line and say that, well, the numbers are increasing this way, what you will see is that here I must have something which is greater than plus 3, and so really there is no space for negative integers. So if I want to take this circle and unwrap it as a number line, this is not a good place to break if we want these 4 binary sequences to represent negative integers. So what is the other logical point? The other logical point is here. So let us see what happens if we break the circle there. So now we are going to break the circle there, and that gives rise to this number line where we start off with the binary sequences with the blue MSB of 1, and then we get the binary sequences with the red MSB of 0, and these we already know are +0, +1, +2, +3, because we want to treat the MSB as the sign bit, and when the number is positive we just want to treat the number as it is an unsigned integer. So now the question is that given this number line, clearly we can find out the direction in which the numbers are increasing, that is the increasing direction. So now what negative numbers, what negative integers should I place here so that I get an increasing number line, I get consecutive integers, and I am also able to represent negative integers. Clearly the choice is obvious, this will be -1, -2, -3, -4, and you can see that this is now consistent with the increasing direction. I have represented consecutive integers and all of them are increasing in this direction. So this is what motivates the 2's complement representation. We are going to try to represent negative integers such that this corresponds to -4, this corresponds to -3, this corresponds to -2, this corresponds to -1, because this allows us to break this circle at this convenient point and then treat this unwrapped circle as an increasing number line. So this is the picture that we have seen earlier. Along the circle I am going to put -4, -3, -2, -1. So this gives me one completely increasing sweep as I go around the circle in this direction, and of course at the end when I come back from +3 to -4 there is a wraparound. In terms of our previous picture, the number line picture, this is really going back from this end to this end, right, 0, 1, 1 to 1, 0, 0, +3 to -4. Okay. And it is easy to see that we can now represent 8 numbers using 8 combinations of 3 bits, so there is no wastage and we have only one representation of 0. Now an interesting question that comes here is that when the numbers were positive we could just read off the numbers as if they were unsigned integers and put plus sign before to get the signed integer. Now when the numbers are negative we have this strange thing that 101, which as an unsigned integer would represent 5, and if you just look at the magnitude which is the bits in black, it would represent 1, but we want this to represent the signed integer -3. Similarly if you look at this number 111 as an unsigned integer it would represent 7, if you just look at the magnitude which are the bits in black it would represent 3, but we want this to represent -1. So a question to ask is that can we have a mapping of the binary representation to the magnitudes of the negative integers. So I would like to go from this 1 to 1, I would like to go from this 10 to 2, from this 01 to 3 and from 00 to 4. So how do we come up with this mapping? So this is our desired mapping when we are using 3 bits, 1 should map to 1. Remember I am just interested in the magnitude now because the MSB has already told me that it is a negative integer. So I want 1 to map to the magnitude 1, 10 to map to the magnitude 2, 01 to map to the magnitude 3, 00 to map to the magnitude 4, and while 10 as an unsigned integer does represent 2, but 01 as an unsigned integer does not represent 3, similarly 11 as an unsigned integer does not represent 1, so we need to come up with a more sophisticated mapping than just reading off this binary sequence as an unsigned integer. Now the first observation we have is that if you look at this 1 over here, which is actually coming from here, right, these are the negative integers and here the magnitude is represented by 1 as an unsigned integer represents 3, however we want it to represent 1. So this 1, what we want it to represent, can be thought of as 4 minus 3. Similarly 10 as an unsigned integer represents 2 and we want it to represent the magnitude 2, so it can be thought of as 4 minus 2. Similarly 01 as an unsigned integer represents 1, we want it to represent 3, so it can be thought of as 4 minus 1, which is 3, and similarly 0 0 as an unsigned integer, it represents 0, we want it to represent 4, so it can be thought of as 4 minus 0, which is 4. So this basically tells us that really if we want to get the magnitude of the unsigned, if we want to get the magnitude of the negative integer from this binary representation in 2's complement, we can just look at the bits that claim to represent the magnitude, we can find out what it represents as an unsigned integer and subtract that unsigned integer from an appropriate power of 2. What was the appropriate power of 2 here? It was 2 squared, because this is the largest magnitude that you can represent using 3 bits in 2's complement. 4 is the largest magnitude that you can represent in 3 bits using 2's complement. So we want 4 minus 0 equal to 4 at this end, and that is why we are subtracting from 2 squared, which is 4. Yet another way to think about this is to say that you look at 1 1, which represents the unsigned integer 3, flip all the bits, you get 0, and then you add 1 to it, and that gives you the magnitude that you want it to represent. You look at 1 0, which represents the unsigned integer 2, but you want it to represent 2, so flip all the bits, you get the unsigned integer 1, then add 1 to it, you get 2, and so on. 0 1, which represents the unsigned integer 1, but you want it to represent 3, so flip all the bits, you get the unsigned integer 2, add 1 and you get 3, and so on for 0 0 as well. 0 0, when you flip, you get 1 1, which represents the unsigned integer 3, you add 1, then you get 4. So if you look at these two ways of computing the magnitude of the negative integers, you see that one way of accomplishing this, basically finding out the difference of the magnitude represented by the black sequence of bits from 2 squared, or from that appropriate power of 2 if you have higher number of bits there, is really to go like this. You can flip the bits, find out the decimal equivalent, and then add 1 to it. So this is what we can do if we are asked a question that can you find out the magnitude of what this represents in 2's complement. So there are two ways. In both ways we will first look at the MSB, figure out that it is a negative integer, and then what we could do is we could look at the rest of the representation, flip every bit, find out what it represents in decimal, add 1, and then the absolute value is 9 in this case, and so the answer is minus 9. Alternatively, we could also solve the same problem in the following way. The MSB is 1, so it is a negative integer. Now to get the absolute value of this, you ignore the MSB, so you get decimal 7, and then you say I am going to subtract 7 from 2 raised to 4, in which case I get 9. Now where did this 2 raised to 4 come from? This is the number of bits in the magnitude. There are 4 bits in the magnitude, which is the total number of bits minus 1, because the total number of bits also has one sign bit. So in this case also the answer is minus 9. So in summary, we saw the rationale behind 2's complement representation, and we saw two simple ways of arriving at the magnitude of negative integers from 2's complement representation. Thank you.